Okay, so the algebra of series. So remember our goal is to learn how to approximate functions the best we can, but functions there's algebra of functions, so you can add functions. What about their approximations? Turns out then if you can add functions, you can add approximations as well. So then the whole algebra of functions as well as numbers is matched by the algebra of their approximations if we can prove it, and that's the step in that direction. So if we have a sequence and a real number, and we have then that sequence forms a series, and if that series converges, then the series of multiples of those numbers C, A, N also converges, and beyond that they are related by an obvious relation where it is as if that number, that multiple coefficient is taken out of the summation sign, even though there are infinitely many terms of them, and placed in front of it. Okay, so that's the multiple, that's the constant multiple idea. Okay, so you can illustrate that with, what does it mean to multiply a series by a number, and we can just try to do something like that with say this one. So how about okay, so suppose this is our series, and it continues on to infinity. So what does it mean to multiply it by 2? So what does it mean that if I say that C is equal to 2, the whole sum is sum AN is here, okay, and each of these is AN. So A1, A2, the bar is that, and this is say AN, and this process continues on with the into infinity. So all of these are being added infinitely many times. So what does it mean to multiply the whole thing by 2? It means that we just, what do we do with this picture? Oops. What should I do with this picture to illustrate multiplication by 2? Stretch vertically by 2. So I just in the paint allows me to do that. So I just go to resize, and then I go to the vertical stretch. So vertical by 200. So maintain aspect ratio I have to eliminate, and I just replace vertical with 100 with 200. Okay. That's it. So the whole thing has been stretched by 2, and what happens to the each bar? It is multiplied by 2. That's the idea. But then what else happens? The total area is also multiplied by 2, right? The area is stretched vertically, and so it becomes twice as large. Only in the vertical stretching, so there is no horizontal change in that matter. After all, this is just summation. Okay, so there you go. That's what the constant multiple rule is. What can happen also is, well, what's the other operation that we can think of for series, and that is matches everything we have seen before, and that's addition. So we have two series, and we want to add them together, and what happens to the series, we can certainly guess what's going to happen, and we can guess that based on the same illustration. So I already have I have only one series. So how about I add I create another one, and then we'll see. So I'll create another one. So this we don't need this, okay, and I'm gonna create a series Bn in addition to this, and then I will add them together in the kind of in that way. So okay, so I'm gonna stretch this slightly in order to emphasize the point that it's a different series. Okay, so it is placed underneath, and I'm going to stretch it vertically by, I don't know, 20%. Okay, so resize, and here I'll make it 20%. 30. Did it stretch? Yeah, it stretched a little. Okay, so this is my series Bn. So all of these now B's. Bn, B1, B2, Bn. Okay, and now if I want to put them together, then if I want to add them together, so add the two together component-wise. So An will be added to Bn. Sum An plus Bn. Okay, so I take the two, and I'll just try to, well, let me take the bottom and let me place, if I can pull it off, one on top of the other. I'm not sure if it is doable. So this is Bn. I'll try to take now An and place it on top. So I have to, what I'm supposed to do here now is to shift the top series one by one, and sort of, it's like a stack of books drop down, so that it takes the shape, the bottom takes the shape of whatever the curved shape that we already have. So it's a bit hard, but I'll try it anyway. So like this. So I take this one and I place it right here. Okay? And then I take this one and place it on top here, more or less. Okay? And the next one, like this. And I'm doing it one by one, forming a new series. Forming a new series like this. Yeah, I can do better than that. Okay, as you can see, the new series gradually appearing from this. So one by one, each of them is placed on top of the new one is, An is placed on top of Bn. So each term here then becomes, this is A1 plus B1, the second one A2 plus B2, and on, all of these are added together. That creates a new sequence, a new sequence naturally, and then if you add it together, then what's going to happen is what happens to then the areas, the total areas are also added together. Okay, so it continues on like this. So the new series looks like this. And what is that series equal to over here? It is equal to sum An plus sum Bn. Okay, as you would expect, but the caveat is always the same. It always only algebra works when you're dealing with numbers. We don't usually do algebra with anything else. So especially if you're speaking of limit, that limit does not exist. You cannot do algebra with something that does not exist. So only under the assumption that both of these areas actually are meaningful, they are numbers, then you can add them together in that way. Okay. Otherwise, the theorem fails, and we'll have examples of when it does fail. So that's the idea. The formula is on the right, and we just have to state it appropriately with all the caveats explicitly spelled out. Okay, so they are spelled out here for the previous theorem. So as you can see it here, I have convergence, then so does the other one. So that's the caveat. The caveat is the assumption rather than and then there's a punchline. So the punchline is that the formula is the punchline. Okay, but if you remember the formula and remember the caveats, that might be a problem. So okay, so it's very similar. The sum rule for series. So sum rule for series. So once again, we have two sequences, An, Bn are sequences. Okay, and then we assume that's the caveat. Suppose sum An and sum Bn converge. Okay, that's the caveat, the condition of the theorem, and then we say then so does the sum made of the new sequence. Sum an plus bn. You can always form, you have two sequences, you can always form a new sequence, an plus bn. Whether or not it converges, it depends. Whether or not its series converges is also, it depends, but on what? On whether or not A and Bn converge in the first place. So we say then that it does, and then everything works out. The series, the third series also converges. And thirdly, that's the punchline, is that we have a formula which is about the sum of the new series, and sum an plus bn, sum bn is equal to sum an plus bn. Okay, like this. Okay, so the point is, of course, to be able to do algebra with the series just as much as with their sums. The operations, as you can see, from the four algebraic operations that you have to begin with, when you speak of limits, whether you speak of limits of functions in Calculus 1 or you speak of limits of sequences, as we did in mid-semester here, and then all the four operations apply. And so four operations, algebraic operations, like just subtraction, multiplication, division. Here, however, we have only two, constant multiple rule and sum rule, which is way less than that. As you can see, the sum rule is the only thing that reappears, even though certainly you can difference too. Not only the sum difference wouldn't make any difference. So I could put minus here and it will still work like this. Okay, so that's fine. Difference is really not a big deal operation, because besides difference is addition with the negative sign. Okay, so you can just derive the difference rule from the constant multiple rule and the sum rule. Okay, but what you definitely don't see here is neither product rule nor especially the quotient rule. So for example, if I have series A and Bn, and then can I combine them together by multiplication? Okay, so right now I combined them by addition and it worked out fine. We were able to illustrate it, but why can't we combine these two? Well, so first of all, how about this one? What's wrong with this? Well, remember about behind this sigma, the symbol sigma that stands for summation, there is summation there. So there is a summation. The first term is summation. The second is also summation. When you multiply two summations, what happens? Should we try? A1 plus A2, and I try to multiply it by B1 plus B2. What's going to happen? A1, B1 plus A2, B2. What's wrong with this?
That series would be infinite.
What?
It would be infinite.
Well, they're infinite, yes, but the problem is not about infinity, actually. I suppose there are only two terms. Let's forget about this altogether. There is nothing beyond it. What's wrong with this picture?
A1 also has to be multiplied by B2.
That's right. You cross multiply. So if you have only two terms, not infinite many terms, just two terms in each, when you multiply, you're not going to get 2 terms, you're going to get 4 terms, right? So the missing ones would be A1, B2, and A2, B1 at the very least, right? So it will be 4 terms, and when you expand it to 3, it will be 9, in 4 it will be 16, and so the that whatever we got on the right over there, that does not make any sense whatsoever, because once again we only multiply line terms A1, B1, A2, B2, which it only gives you not the half but what is the square root of terms. So instead of having 9 you have 3, instead of 16 you have 4. Okay, so so that is not, we can't even start discussion of convergence, because we have not formed the series that could possibly have a chance to match the series on the left. So it is possible. It just the formula becomes very, very complicated, because you start with A1 and you have to multiply term by term by every element in the second series, and then you take the second element in the series, in the first series, and multiply by the rest of them. So it's like this. That to have a chance to work it out, it will be A1 multiplied by Bn, and then you add A2 multiplied by Bn, and A3 multiplied by Bn. So if you try to imagine, it's like a table of rather than a string of numbers, it will be a table of numbers, right? So because the indices, those subscripts, will vary independently. In fact, it's probably a good idea to make that point clearer. You could do this. What if I put here m? It wouldn't make any difference as far as what we have on the left is concerned, but once you start multiplying, you realize that each n on the left does not match anything on the right in the second term. So you have each n is combined with any and each m. Okay, and that's why you have n's here and you have m's there, and then every pair n and m is combined together. Okay, so starting with, and then you go, depending on how many you've got, you will have 2, 2, 4, 9 and 16 and so on. So we just do not really multiply series that commonly, and we stick to these two very simple operations. And unlike limits, when there is no addition, if there is no addition, you can just multiply. That's no problem. That's why we have all those multiple limit rules. But for the sums, that's not the case. Cross multiplication takes really makes things more complicated. Now imagine division. Try to divide one series by another series. So if you want, can you make sense of this? I don't know. I don't think there is anything meaningful to be said about it. So anyway, so just we close this door and they concentrate on those two rules. And well, there's some things to be just an example of what we can do with only those two rules. So just we can combine any familiar or unfamiliar series together in and we don't have too many familiar series just yet. So we are building up the scope of manageable series, starting with pretty much one, the series that we know how to handle, and that is the geometric series. So geometric series converges when the ratio is between -1 and 1, otherwise it diverges. Okay, so that's the only series that we know how to handle. We know its sum as well. This is not a geometric series, definitely. But it is made of two geometric series. So the answer is no. But these two are 1 over 2 to the n and 1 over e and e in -1 divided by 3. Well, actually that's still well, let's cancel 3, so it would not be in the way. So these series are geometric series. So if we could get to them, then we would be able to find the sum of the series. So find the sum, that's the question, even though half of the time half of the time, best we can do is to ask whether or not series converges. But this one is made of geometric series, so it is possible to find its sum. So, so what do? We split it in half by the sum rule first. So it will be 1 over 2 to the n plus the sum e negative n over 3. Okay, by the sum rule. Secondly, this should remind you of how we deal with either sequences or derivatives or integrals. Functions, general limits, split them into simpler pieces, and then continue on simplifying. So, so the first one I will simplify by, well, let me keep the first one intact for now. I'm going to factor out 1/3 by the constant multiple rule in order to have more explicitly written what is that we care about, and that is e to the negative n. Which already indicates what we're facing here. But once again, to make sure that we see that these are geometric series, the one that we're left with, I will put the, I will take the, I want to have the nth power explicit. So, so I took 1 over 2 to the n. It is the same as 1/2 to the nth power. Okay, what do I do with the second series in the same manner? Remember, geometric series is r to the n, so, and where r is the ratio, so that's geometric. I need to identify what that r is, and I did. So the geometric series for the ratio for the first series is 1/2, and what about for the second one? So I'm supposed to have this sum r to the nth power. I just need to tell what that r is. So what is r in for the second one?
It would be e.
E what?
The r would be the e.
No. What about the negative sign? Negative n.
E to the negative.
That's right. E negative first, or 1 over e, same thing, that like this, okay? So then r is equal to 1 over e. Then we are going on to the theorem about geometric series. Both of them are between -1 and 1. So both converge. And we have a formula, so the summation is 1 over 1 minus r whenever the ratio is less than 1, or be between -1 and 1. And so what we end up with is the first one is 1 over 1 minus 1/2. The second one is still 1/3, and then I will have 1 over 1 minus e, 1 minus 1 over e. Okay? So that's the answer. The thing that is missing is, so find the sum, we found the sum. It is a number. You can simplify if you like, but it really doesn't matter. What remains to be worried about is that how we skipped, how we applied the sum rule and this constant multiple rule. Whenever you do that, you have to verify its conditions, and both of them have conditions that require the series involved. This is the sum rule, and then that caveat that I keep mentioning is that the series that you start with have to converge to begin with in order to justify that transition, in order to justify the punchline, which is the formula. And we apply the punchline, the formula, and but we did not verify that, we did not make a build-up, we did not verify that it is applicable. So at that moment, so if you are willing to retrace your steps, and you should, and realize that we actually did do it, but just too late, not too late, but then you can say, well, turn around and use that information that you've got, and you justified it here by saying that, justify the application of the sum rule and the constant multiple rule by saying that these series converge. After the fact. So we did this transition provisionally. We applied the sum rule and the constant multiple rule provisionally So pending proof of the convergence of the resulting series. Then when we went through all the computation, we realized that the series that we're facing in this line over here, they are indeed convergent by the geometric series with appropriate ratio. And then that provisional provisional nature of our computation was eliminated, and we are now fully justified. Okay, and the answer is then not only found, but it is also justified. Okay, so once again, so we make a little bit of a circle, but it is if you do it this way, it is justifiable. Okay, so we do need to discuss convergence. We have been discussing convergence. There is always behind it is discussion of divergence. So we have to make sure that we understand divergence in order to contrast it with convergence. So it's easy to imagine what could have happened here for us to fail. So for us to fail, let me copy this and see what can happen. Okay, so I'm looking at the same problem we just solved. And now imagine, hypothetically, I modify the problem slightly. Okay, so what I'm going to do is I'm going to remove that negative sign. I'm going to remove that negative sign. This one. So remove. It's not there anymore. Okay, so what changes? Not much. This still works out. These are still geometric series. And we still don't know the answer. We still don't want to go through these same steps. And we do. There is really no much difference. We still want to apply the sum rule and the constant multiple rule provisionally, pending the approval of the convergence of the series, and everything works out fine in the exact same manner, and then we arrive to this line over here, okay? And then what do we see? So instead of 1 over e, we end up with e. So this is gone. It is e to the nth power. So my ratio then is equal to e. What does it tell us? What do we know about if the ratio of a geometric series is e? What do we say? What do we know about it? It's not between -1 and 1, so e is larger than 1. But so what does it mean? The theorem tells us more than just. It describes the case of r between -1 and 1, but also it tells what happens when it is not there. What is the answer? It diverges, right? So if it's between -1 and 1, it converges. Otherwise, it diverges. So it is larger than 1, so it diverges. So it diverges, and then what does it mean? It means that these green arrows that I drew, they are gone. So this is all gone. I have to remove this altogether because the first one, by the way, still converge. They not both. So I remove this, and the first one converges. The first one converges the same series, right? So r is equal to 1/2 less than 1, so it converges, but the second diverges. Okay, so the second diverges, and that is pretty much a nail in the coffin because it means that our application of the sum rule and the constant multiple rule was not justified. Okay, so it means that where are we? We are nowhere. We are back to this initial place because the sum rule is not applicable. We have a series, and we want to try to split it naturally to keep it simple, to make it simpler and analyze separately. But those two pieces, one of those pieces was a divergent series, and what divergent means that expression over here is at best At best, this one is infinity at best, and it is actually. But at worst, you can simply say that sometimes it simply does not exist. Remember that that's series or sequence -1 to the n. It is not even infinity, so it is less than that. It simply does not exist. Regardless of that, it is in fact, whether it is infinity or not, as long as it's not a number, as long as there is no convergence, the sum rule does not apply. Okay, so once again, sum rule does not apply. This is not important anymore because, well, we cannot speak of convergence of what the sum is if there is no convergence in the first place. So, and then we are back where we started, and we have to look at it separately. And unfortunately, sum rule does not apply. So, well, and so if it does not apply, we cannot apply it, and so we are back to the start. However, we could try to guess what the answer should be. In this particular case, in fact, once again by the theorem, what can we say about the second line? In the second line, we have two series. One is convergent. The second one is infinite. Okay, so the first one is equal to whatever number is. So it is less than infinity. It is a number, the first series, convergent. The second one is divergent, and it is infinity. So what can you guess about the outcome? Two series. So I'm looking at the second line. Two series. The first one is convergent, the second one divergent. What would you guess about the behavior of the original one?
The outcome would only be the first function, or the first summation bigger than the second summation.
The first summation is bigger than you mean the first line is bigger than,
So like while it's still diverging at infinity,
yeah.
it's your outcome is only going to be just larger than the first summation, or it's going to be that much larger than the second summation. So it's going to be slightly larger than the second summation's infinity.
Well, if it is infinity, what is larger than infinity?
Right.
Okay, so that's a good question. So that's well, you know the answer. Anything larger than infinity is what? It's infinity. So the answer is infinity, right? So if you try to do, and it is sometimes allowable to do algebra with infinities, then the answer would be for the second line would be infinity. So infinity plus a number. Let me try to write it up. The algebra of infinities, it is possible, so a number plus positive infinity is positive infinity, number plus negative infinity or minus infinity is equal to, is negative infinity. Okay, then if you add two positive infinities, you're going to have positive infinity, and so on, right? No, not so on. I don't want to say so on because you might well wish to do the you want to subtract, say plus infinity minus plus infinity, and what's the answer for that? How do we describe this? Remember limits. One limit goes to infinity, the other one goes to infinity. You subtract them, what's the end result? It is indeterminate, right? So indeterminate in a bad sense And indeterminate means that I treat it as a limit, and there is no way around it. So the idea of this is that sometimes you cannot you treat infinities as if they're quantities, and you can do algebra with them, and sometimes you can't. But such as subtracting infinities is in fact indeterminate in that sense, and you can make sense of it if you treat it as a limit, or rather two limits, and then try to figure out what it is. And the indeterminate expression might lead to any outcome possible. It could lead to a limit, it could lead to infinity, positive infinity, negative infinity, or it could still be a limit. That limit might not exist either. So all of these possibilities are there, and you would have to find them out by treating this, where you got to go back and see where those infinities came from, and then based on that find what it is. So if you don't want to make a circle, that is on the right is inevitable, but on the left it might not, and so you just when you end up with infinity, which is pretty much where we are right now, right here, this is where we are. We made that step from first line to second line, and we split this limit into two, and then we're trying to figure out what that sum is, and it makes sense to justify this whenever possible, that a number plus infinity is infinity. Okay, so without going back to the original limit or the original series. Okay, so we just need to state it appropriately for a theorem as a theorem in order to justify the conclusion that we already have over here, that the answer here is infinity. Okay, so we just let's just state it. Well, I already stated it as this, but what you could what you could describe it is a comparison rule. Comparison rule of divergence. Yeah. Okay, so we compare two series, and one of them diverges. Okay, so I have, say, Sn larger than or equal to Tn. So we have two sequences, and there's this inequality between them. Okay, and then there it is possible that one of them is infinite and the other one is not. So some Sn could be, say, minus infinity, and then some Tn is minus infinity. So whenever we can conclude one about the other, and then it's possible that it is equal to positive infinity. So I want to put something here between these two, appropriately drawing conclusions from one to the other. So if the series, these series, so we have two sequences, and there was four series, and we have an inequality between them. So one is larger than the other. The first one is larger than the other. So then if, however, looking at the first line here of these two, if the first inequality, first series Sn diverges to negative infinity, what does it tell us about the other one? So you can think about these in terms of areas. Again, in the area, let's say we have most of those bars lie below the x-axis. So when we start to add them up, they add up to negative numbers. They go small and small and small, and Sn goes to negative infinity. In the meantime, Tn lies above Sn, which means that when you add these numbers, no, Tn lies below. So this is a picture. This is Sn, and this is Tn. Okay, so if summing up Sn's goes to negative infinity, then it is inevitably implies that the same thing happens with Tn, right? Because it is smaller. What about the second line? If the larger one goes to positive infinity, what does it tell us about the other one? So be careful here. So once again, this picture helps. This is pretty much a comparison. While one lies below the other, and here we used it when comparison test or comparison rule. If one is finite, then the other one is finite. So if the yellow area is not infinite, then so is the purple one. But what if one is infinite? What can we say about the other one? So the larger one is infinite. What does it tell us about the smaller one? Right. So what's the answer? It doesn't tell us anything, right? So it could be infinite still. It could be finite, or it could not even exist. It could oscillate up and down. So how do we make sense of the second line then? What symbol should I put between those two? Going in the opposite direction, right? Like this. So if the smaller series goes to positive infinity, then inevitably the larger ones does too, right? Okay. So so if we accept this, it certainly needs a proof, but if you accept this, then we can go back to this series and then explain this line, why this line adds up to infinity, because there are two series, and one of them is then we can justify this conclusion because this series is infinite, and then it is smaller than the original series, right? As it was suggested, right? It was exactly what was suggested just a minute ago so comparing the first and second line. This is nothing about a number, but it is a positive number. So that infinite series in circle is combined with that number, and which makes the whole series larger, and larger than infinity is infinity. Okay, so that's the second line of our comparison rule applies, and that's why the original series diverges to infinity. Okay. So as you can see, it is harder to figure out when you encounter divergent series. Then there are many cases to consider, especially when you have something nasty as this. For example, it's not nasty, but it kind of a simple. Say 2 to the n minus 2 to the n. What is this? It's not a trick question. It is 0, yeah. So a bunch of zeros, and what's the sum of the series made of zeros? Is 0. Okay, but where the things might go tricky, it might be more complicated than that. So this was easy to see that it is 0, so we knew what the answer is. But it might be more complicated than that, and you don't see it, maybe complicated formulas, and that cancellation might not be visible. And then what you try to apply the constant multiple, the sum rule, right? And you have sum of 2n minus, well, actually it works out correctly. No, and then you end up with sum 2n, and both of them are divergent. Okay, and then each of them is infinite. Okay, and then at that point you have to recognize the problem as a subtraction of two infinities, and so it does not fall into the category of algebra with infinities because it's not allowed. This is an indeterminate expression. And with that indeterminate expression, then the explanation of how we handle indeterminate expressions, we go back to the original limit, and remember, series is a limit, and then evaluate the original limit. And so if you go back after that indeterminate expression has been identified, you go back to the original, and then you go back to the limit, and then you how do you handle that limit? You might have to do some algebra, and if you do, then you might actually simplify the expression and realize that there is a cancellation, and you find the answer. But infinity minus infinity is not necessarily 0 or anything specific. Okay, so this is indeterminate, so it brings us back to the original limit. Similar idea exists for comparison rule for divergence. This one, that's for comparison, but then there is a divergence of the sum, divergence of the difference, which we just discussed. Where is it? Okay, so the sum rule for divergence so we have a sequence Sn, we have two sequences. Okay, and then now suppose Sn converges, the sum, not the sequence, even though the rule applies similarly to sequences, but if Sn converges and Tn diverges, then the series of the sum made of the sum of these also diverges. Okay, so sum rule for divergence, and once again, as you can see, sum rule of divergence. If you compare it to sum rule for full convergence, you had two convergence series which produced a convergence series. And then if you try to think analogously, you might say, well, let's take two divergent series, and then their sum should be divergent. But we already know that's not the case, and the example is right there. So the sum of two divergent series is not necessarily divergent, because there can be cancellation, and then you end up with just about anything you can imagine. Same thing is for the constant multiple rule. So constant multiple rule for divergence. Well, actually, it is simpler. It is simpler. You can probably guess what this is. So once again, we have Sn a sequence. We have a C not equal to 0, and then if we suppose that sum Sn diverges, then so does the sum of its multiples, as long as it is not 0. Okay, so if you multiply by 0, you end up with a 0 sequence, and then 0 series, and you have 0. But if it's not equal to 0, then it is, you just shrink, you take the infinity or divergent sequence and shrink it, so it remains divergent. Okay, so we'll assign the homework later today.